for this kind introduction. And it's a real pleasure for me to be present at this meeting honoring Vladimir Orevkov, whose works I encountered very early and I always admired them. And you will see in a minute where there is a connection between my work in proof theory and what Orevkov did earlier on. So the title of my talk is just Logic for Exact Real Arithmetic. And that's one application of logic in a very concrete setting where one wants to use proofs to have interesting algorithms which come with a verification that they are correct and meet their specification. The whole thing is joint work with a PhD student, Franziskus Wiesnet, here in LMU, jointly supervised by Peter Schuster and myself. Okay, so let's start. So proof have always two aspects. First one is that they guarantee correctness, which we certainly want to know, but they, in addition, may also have computational content. And I'm essentially interested in this talk in analyzing and obtaining the computational content of proofs. So what we do is we address this number 2 here and use a BHK interpretation to extract programs from proofs. Now, what is the peculiar properties of this interpretation? Well, first of all, the extract that we extract from a proof, that's a term in the underlying theory. So that's something which is different from what's common in COC, for instance, where people extract a program in some programming language, ML or scheme or whatever it is. And then since you are outside the formal theory, you have a problem of just proving its correctness, because you can prove about formulas in the theory, but not about programs. So the feature of the approach that I'm advertising here is that what we extract from a proof of its computational content is a term in the underlying theory, which means that we have a framework to formally prove its properties. And you will see some examples at the end of the talk. Another important issue is, where does computational content arise? So normally one says that's happening in an existential quantifier. The approach I'm following here is slightly different. So the only way where computational content arises in a formula is when you have inductively or co-inductively defined predicates. So a formula, there is an x such that a of x in itself has no computational content. The content is certainly not the x. That's not allowed here. But we have to relativize that x to some predicate, and then the content of that statement is the computational content that of the predicate saying that x is in a certain predicate. Okay, so what I intend to do here in particular is to look at proofs in constructive analysis in the sense of Bishop's well-known text. And from these proofs, I would like to extract programs that operate on stream-represented real numbers. So let's look in some more detail what's going on here. So first of all, I like to keep the underlying logic as simple as possible. So I use what's called minimal logic, and I use a natural deduction system as is common in Gensen-style proof theory. So what does that mean? First of all, we have introduction and elimination rules for only 2 logical connectives. These are the only ones in our setup, namely implication and universal. So in that sense, the strive for simplicity I certainly share with Lefebvre-Lemaitre. The reason for picking these operations as, or logical connectives as basic, is the closeness with lambda calculus. Of course, you may ask, what is with the other connectives, like disjunction or conjunction or the existential? Well, we can view these predicates as inductively defined. That's an old insight, particularly stressed by Pierre Martin-Löf. And then we just use elimination and introduction axioms for these co-inductive predicates. So that's one way to include these connectives into our setup. Now, what are proofs? Well, I already said we just have introduction and elimination for implication and universal, which means that proofs are just can be seen as proof terms with formulas as types. And that means the proofs we have to deal with are essentially lambda terms with constants. And in such a setup, normalization is an essential aspect or tool because it has many aspects. It allows us to eliminate use of lemmas in proofs, which is necessary when we really want to look through the lemmas and see what's going on, and also to evaluate realizers, which we will look at later on. So this issue of normalization is just what connects me to Vladimir's work. Certainly important that normalization is an efficient operation. Again, it's needed to simplify terms in formulas when you use a proof assistant to interactively develop formal proofs, which is what you have to do when you want to extract programs from proofs. Handwritten proofs are not good for such a thing. And then when you sit in front of the screen and you have a formula to be proven, then the term part of that formula is normally the one that is most difficult to deal with. And there normalization helps if we just can simplify terms and normalize parts of the term until they are reduced to a more easy to grasp and to handle term. Another use of normalization is we want to evaluate the realizing terms that are extracted from proofs. I mean, remember that the realizing terms are terms in our official term language. And when we want to calculate or see what the result is, we need to evaluate these realizing terms. Now, it's well known that for type lambda terms, normalization is super exponential. That's an old result of Rick Stadman. And he did it in a very pure lambda calculus without constants. And this is where the work of Vladimir Orlov comes in. He has a different proof of that result, and in fact, a more general one, where not only pure lambda terms are looked at, but also constants. And that's absolutely crucial to make things simple and useful in practice. So the paper of Orlov is in Sapitsky of 79. Now, let me start with the talk proper. So I will present you a certain arithmetical theory, some variant of HA omega, and formalize some proofs on real numbers in such a theory, and then in the end we'll extract computational content of these proofs, and they will give us interesting algorithm on stream represented real numbers. Before doing that, I'd like to stress that in the underlying theory, I take a kind of old-fashioned approach, namely I first consider a model or construct a model and then design the theory in such a way that it just helps us to prove interesting facts about that model. So the criterion for which axioms to accept is their validity in the model. And in our case, we are interested in infinite data of base types, because later we want to represent real numbers as streams of signed digits, which is computationally very useful. But these are infinite objects and they don't fit in standard models of arithmetic. So for this purpose, I just look at a base type of list of signed digits. And as signed digits, I take -1, 0, and 1, and I write -1 with an overbar. And now, what are the objects that I would like to talk to? They can be seen as total or as co-total or as neither of the two, but still available. And I call these general things partial. These are strict inclusions. So I mainly will work with examples here and don't try to give you formal definitions. So the total object in our list of signed digits would be, for instance, a list consisting of 4 elements, 1, 0, 1, 0. And now a co-total object is again a list, but now of infinitely many objects, 1, 0, 1, 0, 1, 0, and so on. But it never stops. And then we look also at general objects, which are neither total nor co-total. And we can look at a partial object as a deductive closure of something which one can call a finite consistent set of tokens. That's terminology due to Dana Scott, and I will come back to that a little later. To give you an example, here in the second line from the bottom, if I just know about an object that the first element is a 1, I don't know anything about the second, and the third element is a 1 again, such a thing is a token. So it's a simple finite piece of information on some abstract object in our type of infinite lists of signed digits. Just asserts that the zeros and the second element is 1. Now, when working with such infinite streams, the main tool will be something which is known under the name of co-recursion. And here I try to give you a short picture of what that means. So it's called the co-recursion operator. And to understand it, it's helpful if you just look at the type of this thing. Now, this type is spelled out here in this shadowed line. And its main tool is the middle type, which is called the step function. So it takes an object of type tau and produces an object of a sum type. To the left, you have the unit type. To the right, you have the sum of the natural numbers, and then this same type tau again. And then you have an initial argument of type tau and a final argument that is the natural number. So it's not the recursion operator that starts from the natural number, but it is the co-recursion operator that has natural numbers as values. Now, to understand what it means, just look at this displayed equation here. So if you apply our co-recursion operator to an initial object x and a step function f, then the only thing you can do is to apply f to x. And then you have one of these 3 cases listed here. So you may end up in this unit type called dummy, and then you spell out the initial constructor of the natural numbers, which is 0. Second possibility, you may end up in this n part here. So first go right and then the left. Then you also stop. You just take the successor or the unary constructor of the naturals and apply it to the n that is part of what you are given from the applying f to x. And the interesting case is the final one. If you go twice to the right, then you get a tau object. And then what you do is you spit out the constructor successor, and then you make a co-recursive call. That means you apply again your co-recursion operator, but now to this x prime, which you were provided, and again with the same step function. If you look at these equations here, you see as a rule, this whole thing is non-terminating. But still the constant, this constant, or this rule denotes a constant, or it is a constant denoting a partial object in our model, in fact, an infinite one. Now let's become a little more precise of what the model is like. We use so-called information systems introduced by Dana Scott originally to represent the objects of our model. So types are built from certain base types, like these infinite streams of objects. They are free algebras generally by the formation of arrow type, tau arrow sigma. Now, what are formal neighborhoods? Well, they are finite, in an obvious sense, consistent sets of tokens, which is quite clear what that means in the case of base types. But it's more delicate if you go to function types. So what is a primitive piece of information on an object of a function type? Well, it's a pair u comma a, where U is a formal neighborhood. That's a finite set of tokens, which gives you a certain information on the argument. And then you have a single token A of the value type sigma. And the idea is if you know as much as is expressed in U on the given function, then this is sufficient to know that the token A is part of the value. So these are tokens of an arrow type, and now a formal neighborhood is just a finite set of such pairs, U comma A. And you want to understand that as a function, so you have to say what it means to apply such a formal neighborhood to another formal neighborhood of the argument type, called U. And this notion is again very natural. So what you get out is a piece of information, a formal neighborhood of the value type. And it's just a set of all these AIs with a property that the left-hand side, UI of the corresponding pair, is entailed, some kind of a consequence relation from this given argument environment U. Finally, this model is known under the name partial continuous functionals. As I said, it was originally designed by Dana Scott in a paper in the 70s, and then by Yuri Yershov. He has a nice paper where this name partial continuous functionals appears in the title, because it's a model C of partial continuous functionals. So what is such an animal? Well, it's a consistent and deductively closed, possibly infinite set of tokens. So these are the objects generally our model is consisting of. A nice feature of this approach is that it's very easy to define what a computable function is, because it's given as a set of finite things. So we say such an f is computable even only if it is recursively enumerable. And also this is name, this part continuity of the name has a rather easy intuitive understanding. So consider two things, f and x. F, both are infinite objects, f of a function type and x of the argument type tau, and assume that you have an approximation to the value f of x, call it v. And then continuity means that we can find approximations w of the function f and u of the argument x in such a way that these w applied to u, it's a natural notion of application for formal neighborhoods, approximates the value f of x, and it is an approximation that is more informative than the given approximation of f of x. So in a sense, the whole content of the thing is just incorporated in these finite approximations. So that's all I can say in this short amount of time on the model. And now let's approach the formal theory we are going to develop. As I said, the essential tool are the co-inductive predicates, and I'll explain that by an example. So we inductively define a predicate, I call it I0, on real numbers, ordinary constructive real numbers, by two clauses. So the first clause says 0 is in I0, and the second clause says whenever I have already some element x prime in I0, and I have assigned digit d, then x prime plus d over 2 is again an element in I0. So in that sense, I can just build new objects of I0 from former ones. So in that sense, it's an inductive definition. And part of the understanding of inductive definitions is that it is a least set closed under these two clauses. That's sometimes called induction axiom or also least fixed point axiom. It simply says that it's a final display here that if you have a competitor predicate P, which also satisfies these two clauses, which is spelled out in the two premises, then this competitor predicate P is a superset of our original I0. So it's really the least set closed under the two clauses. Now, with any inductive predicate, you have a companion, which I call co-I, and just obtained by dualizing what we had before. So where we had the clauses previously, we now have a closure axiom. First display, it says whenever I'm in Qi0 with an element x, then this x must either be the real number 0, or else it must be composed in the form of x equals x prime plus d over 2 from something that already is in Qi and the signed digit d. So this is the closure axiom, and now again we have a corresponding clause which expresses the fact that this is the greatest fixed point of this closure axiom. This is sometimes called co-induction. And dually to what we had before, it just says if you have another competitor predicate, called it P, which also satisfies the closure axiom, then our Qi0 must be a superset of P. So it is indeed the greatest fixed point. So these are the essential tools to build notions inside our theory. And now at this point, computational content comes in. We can always declare an inductive or a co-inductive predicate as computationally relevant. Then it means it has computational content. And the form of the clauses determines an algebra, which is tells us how the elements which are realizers of this predicate are formed. In our case, the associated algebra will be obviously the list of signed digits. And then the first constructor nil of these lists is just the witness for the first clause, and the second one, the cons, is just the witness for the second clause. Now, remember we had for our inductive and co-inductive axioms, predicates for axioms, clauses, induction, closure, and co-induction. And the computational content of these axioms are things that are naturally associated with our algebra here, namely the constructors, recursion operator, the destructor, and the co-recursion operator. This kind of cases will appear later on in a couple of cases. Now, let's just look in a little more detail at these things. It's quite obvious that the real number 0 can be represented as a stream of the digit 0. And hence we can simplify our predicate I0 by removing the nullary clause. And then we write the corresponding predicates I and co-I. And in what we are going to deal with, we will only need the co-I. And it is co-inductively defined by the closure axiom. It says, whenever I'm in co-I with an element x, then this x can be written in the form x prime plus d over 2, with x prime again in co-I. So that's a single closure axiom, and then the corresponding co-induction axiom is what you have seen before, spelled out in the second display. I already told you that any inductive or co-inductive definition determines a certain algebra. And in our case, associated algebra or data type is just the algebra of streams of signed digits, which is given by a single binary constructor whose type you see at the end. So notice that there are no finite objects here, just streams. So the only objects that you can have in this algebra are infinite objects. Now, the axioms for our co-I are the closure axioms and the co-induction axiom, and they have computational content. I already told you that is the destructor in the first case and the co-recursion operator in the second. Now, in this slide, the types and the computation rules of these animals are explained. So the destructor has type stream and arrows signed digit times stream. And it's the obvious thing. So the destructor of d cons u is just this signed digit d, and as the first component, as the second component, the tail of the stream, the u. And the co-induction axiom has as computational content the co-recursion operator now for streams. And this is essentially what you've seen before as a type of the co-recursion operator, but now it's simplified because we have left out this unnecessary initial object 0. And then the co-recursion operator applied to X and F is explained as before, so I think I don't need to repeat it. The only way to approach the meaning of that operator is just to apply the step function to the argument X, and that is an animal in this product. Gives you the left component, the digit you spit out, and then you either are finished already and give out the tail, or else you make a co-recursive call. So much for the predicates. And now next, I'd like to go to the arithmetical theory with our intended model and where the main ingredients are co-inductive predicates. And it will start from the top of what's going to be developed and then later on explain the notions that are used. And what we are really interested in is the so-called soundness theorem. And what does it say? Well, suppose in a theory, minimal logic based on our model and using co-inductive predicates, consider this proof in a theory consisting of the axioms and the logical rules. And let's assume that this proof is a proof of a certain formula A. And I call this formula R3, R for realizer. So it will be explained later on what that means, but just think of an ordinary formula in a standard arithmetical theory where realizability is not mentioned. And for the moment, ignore that this will be a proof from assumptions. Let's just assume we have this good plain proof of a formula A. Now the soundness theorem says that if we take this proof, M, and extract its computational content, that's something I'll spell out later on. It's called the extracted term of our proof, or the computational content of the proof as determines the language. This is something which is a witness or a realizer of the validity of the formula A. So that's what the soundness theorem says. Whenever I can prove the formula A, and this A happens to be computationally relevant, has some computational meaning, then what we extract from the proof is indeed a realizer for A. So that's what the soundness theorem says, and we will have a look at the proof in a minute and some usage of this proof towards the end. Now we also have to do that for the case A is non-computational, has no computational content, then we just keep the formula. Now, in order to work with such a notion of proofs, we have to relativize this proof to proofs with assumption. Remember, we are doing natural deduction here. So assume the proof is from assumption CI, labeled with UI. And then, of course, we can't prove that outright, but we have to assume that we already know some witnesses or realizers of our assumptions. So this proof that we have there is not an absolute proof, but it's a proof from assuming that we have already given a certain realizer, I call it ZUI, of the I's assumption CI, in case this thing is computationally relevant, and if not, it's just the CI itself. So in this form, the soundness theorem can be proven, and it just will give us later on what we want to know, namely a formal proof that a certain term that we extract from a proof is indeed a realizer of the formula that is proven. The proof will need something which I have baptized invariance axioms, although it appears in many places in the literature already. So constructively to state a formula A just means the same as to say that the formula A has a realizer. That's something that was spelled out, that's at the root of the BHK interpretation, and Kolmogorov wrote a very nice paper back in 1932 zur Deutung der intuitionistischen Logik. And there essentially, that's essentially what he states there. This thing was later taken up by Saul Pfefferman, and he formulated the statement in the form A if and only if there's a realizer of A, and he called it to assert is to realize. Now, in our formal setup, we just restrict these things to ordinary mathematical formulas A, which don't involve realizability. I call them R-free. But the formula itself must be computationally relevant. And then the invariant axioms are just the two directions of the implication of the equivalence above. And I just give you a glimpse of the proof of the soundness theorem, and I will treat the only two cases where the invariance axioms are used. So these are two cases, arrow introduction and arrow elimination. And let's first look at the arrow introduction case. In the special situation when the whole thing that we are proving is non-computational, that's the conclusion of the thing A implies B, and the premise A is computational, CR. And now we need a derivation of A implies B, and in the soundness theorem, because B is NC. And by induction hypothesis, we already have a derivation of B from the assumption that we have a realizer Z of A. Remember, A is computational. And that's what you see in the first proof figure on the right, labeled IH for induction hypothesis. This is something which we have by assumption, a derivation of B from Z realizes A. And now in red, you see the one direction of the invariance axiom, which wants a proof of A to be applicable, but we are given a proof of A. And then we get as a conclusion, there is a realizer of A, and now it just exists the elimination, so which allows us to conclude B, which is what we wanted to have. So that's the first case where invariance axioms are needed. And the second one, that is just modus ponens or arrow elim. Again, in the case that the B here is NC and the formula A that's cut out is computationally relevant. And then the soundness theorem requires us to find the derivation of B. And again, we have an induction hypothesis, which we use twice. First, we have a derivation of the implication, A implies B. And second, we have a proof that the extracted term of the proof N of A is a realizer of A. Now in the display, at the bottom, you see to the right, this proof of ETN realizes A, labeled IH. And remember, we are given a proof of A implies B, and we want to get at B. So what we need is a proof of A. And to get it, we need the other direction of the invariance axioms. We just have this universal formula for all Z. Z realizes A implies A. And we just specialize it to ET of N, which we know. And that tells us, or gives us the implication ET of N realizes A implies A. And now it's just an modus ponens, which gives us this A. Okay. And what I didn't tell you, but should, is what exactly is the meaning of the computational content of a proof of a computationally relevant formula A, what we call the extracted term of M. And since our logic is extremely simple, just lambda calculus with axioms, i.e. the kind of terms that Orfkoff analyzed, this definition is very simple. So we just have to start with what is an extracted term of an assumption. This, of course, is a difficulty because we just have assumed the formula A, so what should be the content of it? Well, at this point, we have to assume that to every assumption variable of a CR formula A, we have associated uniquely a certain term of type tau of A, that's the type of the formula A in the natural sense, and that's associated with the U, I call it ZU. And that's what we define to be the extracted term of the assumption. That was the most difficult thing, and then the other ones are easier. So if we look at the introduction and elimination rule for implication, the first one is lambda abstraction or arrow introduction of A implies B. So what's the extracted term? Well, the interesting case is if our premise A is computational, then we already know an object variable ZU, which is associated to the assumption variable u of a. And this likely will appear free in the extracted term of the derivation m, which will, of course, involve the assumption u. And so we just lambda abstract this zu in the extracted term of m. In case there is zu, and that is a is CR, and otherwise we just extract from m itself. The modus ponens case is the next one. So if we have derived b from a implies b and a, and we want to know what is the computational content of this one, well, we clearly have to distinguish whether a, the premise, is computational or not. And if it is computational, then we know what the content of the derivation m of the implication is and what the content of the derivation n of the premise is, and we just apply the former to the latter. However, very often the premise a, which needs a derivation na, is non-computational. And in this case, it's just simply ignored. So the computational content of m applied to n is just the content of m of the premise n. In fact, that's the reason why the extracted term of a proof normally is much smaller and simpler than the proof term of the whole proof itself, because we can just ignore everything without computational content when extracting. The final two clauses are just concerned with universal quantification and for all elim. And remember, our quantifiers are viewed as computationally meaningless, so we just ignore them. If we want to have to quantify over an x and take into account that x has computational content, we have to relativize this quantifier x to a predicate with content, normally an inductive or co-inductive predicate. So the universal cases are very simple. Okay, now let's just look at a computationally relevant inductive predicate. And I already told you what the extracted terms of the axioms are. There's one particular case which I won't spell out here in detail, but since it's important, I would like to mention that there are some inductive predicates which are non-computational and are given by one clause only, for instance, the non-computational existential quantifier. And they appear a lot in ordinary proofs, and they also have as any inductive predicates, they have an induction axiom. And this induction axiom has as its extracted terms the identity. That is quite important to know that in practice. Now, finally, I'd like to remind you of the particular situation of our predicate I0 here to explain what the realizing variant or realizing version of the such inductive predicates are. I call it I0 super R. So that's a predicate which has now two arguments. The first one is the real number that is an element of an I0. And the second one of type L is meant to be a realizer. So we need to express in our theory what it means to realize a certain inductive predicate like I. So I write U realizes I0x, just in the form x comma u is an element of I0R. And this realizability variant of the predicate I0 is always non-computational, intuitively, because we already have the realizer. And now our theory will deal with such predicates, so we have to know how it's defined. And this is the first displayed formula here, or better, the two clauses. So the real number 0 has as a realizer the empty list of signed digits, quite obvious. And if we just go to the clause of this predicate I0, then we say if we have a pair XU, which is in I0R, and then we make one step into the signed digits. So with the next thing in I0 is x plus d over 2. And the corresponding realizer is S sub d cons u, where S sub d is a signed digit which corresponds to the formula that D is in SD, the predicate SD. So these are the two clauses which are really very intuitive if you think about what realizing means in this setting. And then again, we have an induction axiom which says that this is the least set with this property. And the very same thing can be done for co-inductive predicates just by dualizing these two things. Okay, finally, let me come to an application. So I'd like to design or to look at division of real numbers, and I'd like to obtain a verified algorithm for doing division of real numbers with a signed digit representation of real numbers, which is very useful in practice. So let's see how we can tackle this problem in the setting of a logical theory. The idea for that is taken from a paper of Schiapaglione and Di Gianantonio some years ago. So we just look at x over y, where we assume that y is positive. And we can, by some easy calculations, look at these three different representations of x over y, which use a certain x1, x0, and x minus 1, which are displayed one line below. And the idea here is also for the algorithm that depending on where the x is in our given interval, we just choose one of these representations, and this choice will be done constructively, and it gives us the first digit. And then if we iterate this kind of approach, then we get a co-recursive definition of x over y, and that's what we want to have. So we now, as always, consider the dualization of I, and we also leave out the 0 as we did before. And then the co-I is co-inductively defined by its closure axiom. So whenever we are with an x in co-I, then we can decompose it into a signed digit and predecessor in co-I, and in such a way that x has a form x prime plus d over 2. So that's what you essentially have seen before. And now I'll leave out a lot of stuff here and just state a theorem that we can formally prove in the theory we are dealing with here. And it just says whenever we have two objects in co-I, x and y, and we assume that y is sufficiently positive, it suffices to have 1/4 below y, and moreover that the absolute value of x is less than y, then we can prove that x over y is an element in co-I. So that's a statement that's easily formalized in the language. It has computational content because co-I has, and the formal proof is by co-induction. And what I've displayed here is what we obtain if we formalize a proof and then call it M and then compute the extracted term of that proof. And that's called the computational content of this proof. And this is a certain function, I call it division, of u and v. Think of u and v as streams of signed digits. And the co-recursive definition of this operator is just spelled out in this case distinction below here. And it all comes out automatically from the case distinctions that you need to do in order to prove the theorem. So you see that it's a co-recursive call of the diff itself, so it's non-terminating, and it spits out a signed digit, namely right, which means +1, m, which means 0, and l, which means -1, and then applies this diff again, but to something which is obtained from u and v as aux r double or aux l. And you see what kind of case distinction has to be done in the display to the right. And you also see the look ahead, how far you have to look into the signed digits stream to obtain the result. The final lemma which we need here is the following one. This co-I is closed under shifting a real less than or equal to 0 by +1. And similarly by -1 if x is positive. Again, this lemma can be formally proved, and its computational content is a function in the positive case, which is called @1. And what it does is it takes the first digit of the streams that you are given, and in the case you are on the right already, that means you have already 0, then you just take an infinite list of rights or plus ones. And in the case you are in the middle, you in front add str and then make a co-recursive call. And in the final case, you just turn SDL into SDR. And here the extracted term of the +1 part is spelled out at the bottom. The interesting thing to note is that what we extract is the term involving co-recursion. That's the first line in the display. And the type of the co-recursion is the algebra of streams of signed digit, which is called AI here, into itself. It takes a stream and it just then decomposes the stream into the cases according to the first digit, and you see what it does if it is right, middle, or left. You just always return the right and then make, if necessary, a co-recursive call using in right or in left. Okay, these extracted terms can be evaluated, normalized, and then you can use them to compute. So recall that our algorithm for the diff function is given by the function diff spelled out here. And we can evaluate it, and what we get is a stream. And then, of course, when computing with streams, it's helpful not to use an ordinary functional language like Scheme, which we're using normally, but there is a language called Haskell, which is particularly efficient when it comes to computing with infinite data. So we can translate our extracted terms into Haskell code and run it. And here you get the run times, and it's quite important that what you extract are really efficient codes. So if we divide two real numbers, which are given here by approximations to rationals, so one is 1/3 and the other one is 1/2, and then compute the resulting stream with a certain number of digits, and you see you can even compute the first 100 digits of this division with what you extract from the proof in less than half a second. So it's really fast. And there's another important aspect here which I'd like to stress, and that concerns correctness. You all know that's a major issue in programming to prove that a certain program which is meeting a specification is correct. And that's difficult and almost unsolvable generally if you just start out with a program written by a programmer. If we replace a programmer by a mathematician and let the mathematician provide us with a proof in a formal system, then we can extract from that proof the program, and now let the machine provide us with a soundness proof. So let the machine prove us that what we have extracted is indeed a realizer of the original theorem, i.e. the specification. So if you apply that to our theorem here, this Co-I-diff, it's a command in the underlying proof assistant is called add sound or add a soundness proof, then the system provides this proof, and in the middle display you see what the formula of the soundness theorem is. You have seen that in a theoretical way a minute ago, and here it just says that this Co-I-diff of two streams you had and you had 0, it's in the middle of the slide, that this is indeed a realizer, that this term real or diff applied to y and 3 times x is a realizer of what we is an element that's realized by this stream. And it also gives you the computation rule of our term that we extracted, this Co-I-diff. So again, what I want to stress is this generated formal soundness proof is automatically obtained, and it can, if you don't believe that the implementation is correct, it can also be machine checked, which is also done by the system. So let me conclude. So we have sketched or looked at a certain variant of HA omega, which I call TCF, the theory of computable functionals. And what's the differences to standard treatment of Heyting arithmetic? Well, first of all, it's a so-called, what Schoenfield calls the classical axiom system. So it's based on a model. And the model is somewhat peculiar. We really are forced into partial continuous functionals because we need co-recursion operators and they are just partial objects. So this partial setting, which is normally avoided in proof assistance, is quite essential for the approach here. But it's also doable. And then the main tool in the whole thing is to treat our mathematical theory with inductive and co-inductive predicates. And that's the only place where computational content comes in. Well, we need the well-known concept of BHK, or modified realizability, as Kreiter called it. We need invariance axioms, which really express what realizability is about. And in our setting where we extract into the underlying term language of the theory, we have at least the possibility to do formal soundness proofs, and this can even be done automatically. Well, this application that I told you in the final part of the lecture is the division algorithm for stream represented real numbers, and it can be extracted from a formalized proof, as I tried to sketch. The formal system that we use is the min-log system. You see a reference at the bottom. And the essential point is that we can do our standard mathematics here. We don't have to do computer science. We just treat ordinary real numbers in a constructive way, the style of Bishop. And then, since the proof is done in an appropriate system, what we extract is something that works with streams of real numbers. That's it. Thank you very much for your attention.
Please, questions.
I have a short question, Sladik. Seems like very, very natural and very nice idea. Have you thought of extending it to kind of higher types instead of real numbers to describe functions this way and so on? Because this is a very natural thing based on like what Yershov was doing and what Chernov did.
Yeah, well, the whole setting is a higher type theory. So I said it's a variant of HA omega. So the theory talks about finite type objects, where the types are built from certain base types. It just happens that this application doesn't use higher types in a proper way. So the only point where type level 2 comes in are the co-recursion operators. But if one starts out with a higher type computational problem, which is treated mathematically, one can certainly do that. So there's ongoing work right now on the constructive integration and measure theory based on some recent work of Hajime Ishihara. And in this setting, we are trying to use a similar approach, and this will be a higher type setting, so that will be coming hopefully soon.
Vladik, this is just a short comment from the side. This is, well, thank Helmut for taking seriously the most tantalizing idea of constructive proof theory, namely programming by proving. And the problem in this direction is that you really have to strike a very fine balance between efficiency and convenience. Yes. If you prove in the unlimited mathematical language that what you produce, first it takes quite a while to even compile, but the most important danger is that you're not always have a sufficient control over the efficiency of the program which you're producing. It's a fine program, but if you just do blind extraction, following just the usual realization algorithms, you can easily get a polynomial which is 50,000 degree on the problem, which can be in the usual functional way to be programmed quite easily. So we don't want to lose the efficiency, the control of efficiency. On the other hand, another danger, or the rock you have to steer by without touching, is you don't want to degenerate your business, your activity, into reverse engineering. You have a functional program, you have a good program, efficient program, and then you reverse engineer the proof, which would produce you the comparable in efficiency program. And it takes a very good taste and a lot of courage to do this. And I'm really admiring the effort which Helmut is making. It teaches us all a lot, especially those who are interested in how this idea can be implemented. Thank you.
Yes, thank you for the question. That stresses really two very important issues. The first one, with efficiency, is a very serious one. And it has been largely ignored in the approach to constructive analysis that is prominent at the moment. I think it's a task for the mathematician to just keep in mind when doing or designing proofs the efficiency aspect. But he can do that in the world he is living in. That means he has to think about what are the objects I'm talking about and which kind of case distinctions is reasonable in this sense or not. So I'd like to shift the burden of thinking about efficiency on the mathematician and not on the programmer.
Yeah, sure, of course.
And
it's a remarkably appropriate subject, Helmut. Thank you for picking the very right subject for this particular conference and for this particular group, because in constructivist, the hotbed of Russian constructivism, and this is St. Petersburg, Leningrad group. This is exactly the issues that were the main concerns of these people, has been and still are. Thank you. More questions? Okay, then we 5 minutes break. So it's the 13th or the